Right now, at this very second, there are over 20,000 aircraft in the sky across the globe. Each one broadcasts its exact position once every second. But here's what most people don't know. Every single movement, every word spoken in the cockpit, every decision made, it's all being recorded. And when something goes wrong, these recordings become the most sought-after evidence in the world. But what if I told you that the black boxes everyone talks about aren't actually black at all? They call them black boxes, but there's a reason investigators can spot them in wreckage from hundreds of feet away. Flight data recorders are actually bright international orange to aid recovery. The name we all use is completely wrong. Modern aircraft like the Airbus A350 record 3,500 parameters for 25 hours. Compare that to just 100 parameters in the 1970s. These boxes are built to survive impacts, producing 3,400 times the force of gravity and temperatures of 1,100 degrees Celsius. The technology evolved from Francois Houssinot's 1930s photographic film recorder, which literally needed to be kept in a black box to prevent light exposure. That's where the misleading name comes from. But recording everything that happens is only half the battle. The real question is, how do you find these boxes when they're at the bottom of the ocean? Modern black boxes contain an underwater locator beacon that pings for at least 30 days at depths up to 3 kilometers. And here's the twist. Aviation authorities worldwide are now considering making these crash-proof recorders obsolete. Imagine you're trying to keep track of all those orange boxes, except they're flying at 800 kilometers per hour, 11,000 meters in the air. Welcome to the daily challenge facing air traffic controllers on every continent. Every single day, the world's airspace handles over 100,000 flights. In the United States alone, that's 44,000 flights daily. Europe manages similar numbers across 37 different air navigation service providers. At peak hours, controllers worldwide are monitoring thousands of aircraft simultaneously. Think about that. Thousands of planes, all moving at different speeds, different altitudes, different destinations. And the margin for error? Just seconds. So how do controllers keep planes from colliding when they can't even see most of them? The answer involves an invisible bubble around every aircraft. Standard radar separation is 3 miles horizontally, 5 miles beyond certain ranges. Vertical separation is 1,000 feet below 29,000 feet altitude, 2,000 feet above that. But wait, 3 miles sounds like a lot of space until you realize how fast these planes are really moving. In RVSM airspace, between 29,000 and 41,000 feet, planes can be just 1,000 feet apart vertically, effectively doubling airspace capacity. On final approach, separation can shrink to 2.5 miles. And wake turbulence rules mean small planes must wait 3 to 4 minutes before taking off behind heavy aircraft. In 2024, Europe saw a 40% increase in weather-related delays, with over 70% of all air traffic delays attributed to adverse weather. When weather closes in, these bubbles have to expand, and that's when the delays cascade. But here's the problem with radar. It's old technology. It can only see planes when it pings them every 5 to 12 seconds. What if there was a way for planes to constantly broadcast their exact position? Enter the technology that's revolutionizing air traffic control and letting you track any plane from your smartphone. January 1st, 2020. Every commercial aircraft in U.S. airspace had to be broadcasting its position, or it couldn't fly. Australia had mandated it in 2012. Europe followed. This created something air traffic control had never seen before. Perfect visibility. Automatic dependent surveillance broadcast changed everything. Aircraft now broadcast their exact GPS position once per second, compared to radar's 5 to 12 second update rate. Signals can be received by ground stations up to 250 miles away. The technology provides 21% more airspace coverage than radar. Here's what nobody expected. Hobbyists with $100 computers started building their own receivers. Websites like Flight Radar 24 now track aircraft in real time using crowdsourced networks. For the first time in history, ordinary people could see what air traffic controllers see. But this transparency also revealed a problem, because ADS-B depends entirely on GPS signals, and GPS can be jammed. In regions of political tension, GPS interference has disrupted air traffic tracking. Imagine the vulnerability this creates. The current air traffic control infrastructure in many countries was built decades ago. Some facilities still use legacy computer systems. Many nations have been trying to upgrade since the early 2000s. The question is, why is it taking so long? Modernization projects worldwide have cost tens of billions of dollars. The FAA's Next Gen program alone launched in 2007 with a price tag exceeding $32 billion. Europe's Single European Sky initiative has faced similar challenges. These aren't just technology upgrades. They're complete system replacements that must happen while keeping hundreds of thousands of daily flights safely in the air. Inefficient air traffic control costs airlines an estimated 5 to 10% of aviation fuel globally through holding patterns and indirect routes. The challenge isn't just technical, it's organizational, political, and financial. So what exactly are they replacing, and who's making it work? All this technology depends on one thing: humans making split-second decisions. Air traffic controllers worldwide manage over 200,000 flights daily, but many countries face staffing shortages. Controllers at busy facilities manage traffic that moves faster than highway speeds, with consequences measured in hundreds of lives. Imagine you're a controller at London Heathrow or Dubai International. You're watching dozens of aircraft on your screen, each moving at different speeds. You have seconds to make decisions that affect hundreds of lives. More than 70% of air traffic delays globally are attributed to adverse weather. Controllers must adapt in real time to storms and visibility changes. But what if we didn't need human controllers at all? Some experts are already testing concepts where aircraft navigate themselves. But we're not there yet. First, we need to solve the data problem. Remember those orange boxes at the beginning? What if we never had to search for them again? The technology already exists. Instead of storing flight data in recorders, aircraft can continuously broadcast all data via satellite. Airbus is testing deployable recorders that automatically eject during crashes and float on water while transmitting their position. But there's resistance. Concerns about data security and who has access to real-time cockpit information, bandwidth limitations, the cost of retrofitting fleets. Traditional black boxes have a proven track record. So those black boxes we started with. They might not just change color, they might disappear entirely. The question isn't whether the technology is ready. The question is whether we're ready to trust it. The next time you see a contrail cutting across the sky, remember, that aircraft is broadcasting its exact position once per second, being tracked by systems that cost billions, monitored by controllers managing thousands of flights, and recording every word, every action, just in case. Because in aviation, the difference between a routine flight and catastrophic accident often comes down to a single recorded second that investigators will analyze for months. The invisible highways are more crowded than ever, and somewhere right now a controller is making a decision that will determine whether 200 people land safely or become another data point in a recording.